In today's lesson, we are going to look at our power laws again and looking at some other patterns. So more patterns with powers. So as a warm-up, express each sequence of numbers as a sequence of powers. So what that means is if I have 2, 4, 8, 16, 32, 64, I want to represent these numbers as a sequence of powers. So 2 can be a power of 2 to the power of 1, 4 would be 2 to the power of 2, 8 would be 2 to the power of 3, 16 is 2 to the power of 4, 32 is 2 to the power of 5, and 64 is 2 to the power of 6. So that's what we mean by a sequence of powers, right? It's the same base, and our powers are increasing 1, 2, 3, 4, 5, 6. B, same idea. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of 3 is 1,000. 4, and 10 to the power of 5. C is a little bit different because we're starting at 81 and 27, 9, 3, and then 1. So it might be a little bit more difficult, but if we start at, we know 3 will be 3 to the power of 1, we can kind of work reverse. 9 is going to be 3 to the power of 2, 27 is 3 to the power of 3, 81, if we're not sure, we can check, but 81 would be 3 to the power of 4. And what would 1 be? Well, again, we know anything to the power of 0 has to equal 1, and if we follow our pattern, 4, 3, 2, 1, the next one would be 0. And again, that does follow the rule that we learned in a previous lesson that anything to the power of 0 is equal to 1. So that does fit, and it does fit our sequence here. So what we're going to do is we're going to extend this. So we want to continue this down the other way. So 2 to the power of 4 is 16, 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1, and that's where we've left off. So I want to kind of continue the pattern and go down to figure out what would 2 to the negative 1 be. 2 to the negative 2, 2 to the negative 3, and 2 to the negative 4. Now I want to fill out the rest of this table because what we're going to learn about today is how do negative exponents work. And we're going to use our patterning tools that we've done in the past. What does it change by? Well, 16 to 8, 8 to 4, 4 to 2, 2 to 1. What's the pattern here? And if you take a second, you should see that every time we go down, or every time our power decreases by 1, we're dividing our value in half. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So if we continue that pattern, 1 divided by 2 is 1/2. 1/2 divided by 2, 1/4. 1/4 divided by 2 is 1/8. 1/8 divided by 2 is 1/16. So if we continue the pattern down, those are what the values would be for those specific exponents. Right? So the pattern that is evident in each column, exponent decreases by 1, value is halved. Is halved. So our value is basically cut in half. And we use that to kind of continue our pattern here. So what can we notice about how the exponents, the negative exponents, relate to the value? Right? Because we do see something similar in these repetitions, or in these values, and the exponents. When we have an exponent of -1, it's a half, or 1/2. positive, or the value when the exponent is -2, it's 1 over 4. -3 is 1 over 8. We see that kind of pattern, or we see kind of some comparisons with the powers that have positive exponents. Right? 2 to the power of 1 has a 2, then there's a 4 and an 8. 2, 4, and 8, except it's on the bottom. So there is kind of a pattern here that we can see. And that's going to help us understand how we can deal with negative exponents. So in conclusion, powers with positive integer exponents, so basically positive numbers, represent repeated multiplication. So that's what we've been dealing with powers before. But powers with negative integer exponents, so basically negative exponents, represent a repeated division. So it's a repeated division and not a multiplication. So what we can do is we can see that this rule can also be seen considering the expression b to the power of 0 over b to the power of n, which when we use the quotient rule becomes b to the power of 0 minus n, or b to the power of negative n. What we can also simplify is that in the numerator we have b to the power of 0, which we know is equal to 1. Essentially what that is saying, that's just kind of the theory behind what this rule is. When we have a negative exponent, b to the power of negative n, that becomes 1 over b to the power of positive n. So basically you just flip the exponent or bring it down. Or you could say flip it and it becomes a positive exponent. So that's what you do when you have a negative exponent. You basically flip it or put it underneath 1. So let's take a look at some examples. So we have one example here, 3 to the power of -4. Our rule says we have to flip that. Any whole number is always over 1, so when we flip it, it becomes 1 over 3 to the power of now +4. We can simplify 3 to the power of 4, which is 81. So our simplified solution becomes 1 over 81. You can check on your calculator. Depending on what calculator you have, it's not going to show up as this fraction. It'll be a decimal value, but when you clarify or double check 1 divided by 81, you should see that it's the same decimal value either way. B, 4 to the power of -2. Well, negative exponent, so I'm going to flip it or put it over underneath 1 and make the exponent positive. So 1 over 4 to the power of 2. I can simplify 4 to the power of 2, so it becomes 1 over 16. Two to the power of -5 becomes 1 over 2 to the power of +5. This then becomes 1 over, I can simplify 2 to the power of 5, which is 32. And lastly, 10 to the power of -3 becomes 1 over 10 to the power of +3. So this becomes 1 over, and then 10 to the power of 3 is 1,000. So this is 1 over 1,000. So since negative exponents represent division, we often end up with very small decimal values when evaluating with a calculator. So if we recall the example of choosing a 5-letter password, the probability of that, or the number of possibilities is 26 to the power of 5, because there's 26 letters for the first character, 26 for the second, third, fourth, and fifth. That means that the probability of correctly guessing such a password is 1, because there's 1 correct possibility, and there are 26 to the power of 5 total possibilities. So how can this probability be written using a negative exponent? So if we actually do this division, or as a negative exponent, we could reverse this bring this up and it becomes 26 to the power of negative 5. Because we know when we flip it and it is underneath, it becomes a positive exponent. So if we reverse that and bring it up, it becomes a negative exponent. If we actually evaluate that 26 to the power of negative 5, we get a large, well, not a large, but we get a number in scientific notation. Again, depending on your calculator, but you should be able to convert it to scientific notation regardless. You should get something along the lines of 8.4165 times 10 to the power of negative 8. So what's different now is that we see the exponent on the power of 10 is negative. When we've dealt with scientific notation, our powers have been 10 to the power of a positive integer. This means that the significand is being divided by 10 multiple times. So rather than being multiplied by 10 multiple times, which we saw when we had very large numbers, when we have very small numbers, we're going to be dividing the number by 10. And it works in a similar way. Basically what this means is that I am moving the decimal place 8 places to the left now. Before we would move it to the right, now we're going to be moving it to the left because we're dividing. So in this case, this would become, let me write out the decimal number first, so 84165, and to move it to the left, 1, 2, 3, 4, 5, 6, 7, 8. 8 times. That means the decimal place is now here. I need to fill in these values or these missing spots with decimal or with zeros as placeholders. So it actually means that there's 1, 2, 3, 4, 5, 6, 7 zeros in front. So it's 1 less than what we actually see here because this decimal place has to move 1 in front. So there's going to be 7 zeros in front, and then a decimal, and then a 0 again as a placeholder. So our actual value is 0.00000084165. So again, a very, very, very small number. And can you think now, we've talked about when we might have used very large numbers, but can you think of other applications that involve very small numbers that need to be expressed in scientific notation? So when might we have extremely small numbers? Right? So you don't need to come up with an answer right now, but think about when you might deal with very small numbers where you need to use scientific notation. Just as some practice now, we are going to convert between scientific and standard notation. So again, 4.23 times 10 to the negative 6, that means this decimal place is moving to the left 1, 2, 3, 4, 5, 6 times, which means there will be 5 zeros after the decimal place. Or you could say 6 zeros and then there's a decimal after the first one. For the second one, I want to go from standard to scientific. So I have 1, 2, 3, 4, 5, 6, 7 zeros in front. So this will be 2.4 times 10 to the power of negative 7 because we're dealing with an extremely small number. For the next one, 1.432 times 10 to the power of negative 8, there's going to be 8 zeros. And then 1432, and we're going to put a decimal after the first one. For the next one, we have 1, 2, 3, 4, 5, 6 zeros. So it's going to be 10 to the negative 6. And then my scientific notation is going to be the 1.23 times 10 to the negative 6. Or we're basically removing the decimal place 1, 2, 3, 4, 5, 6 spots back. 6.5 times 10 to the power of negative 3. We're going to have 1, 2, 3 zeros, and then 6, 5. And the decimal place comes after the first 0. And finally, 0.000084 becomes 8.4 times 10 to the power of, and there are 1, 2, 3, 4, negative 5 zeros. Or you could think we'll have to move the decimal place 1, 2, 3, 4, 5. 5 spots back from the standard notation, and then that gives me the exponent. So again, this is looking at scientific notation when dealing with negative exponents. We talked a bit about what negative exponents are and how to rewrite them as positive exponents, and just understanding that negative exponents represent very small numbers, or a division or repeated division, whereas positive integer exponents represented repeated multiplication.